So hello everyone. I hope you can hear me, and this is working fine. Right. Yeah, brilliant. Thank you. Right. So my name is Victor. I'm really excited to be here. This is my first PocketQube workshop. I myself am a very big sci-fi fan, so being part of a community that works with satellites and launches them into space is almost like a dream come true. And a big, as you probably may know, a lot of really seminal sci-fi works deal with things like accessibility and, but basically things being like everyone can participate in. So on a similar sort of note, I am here today to talk to you about using open source tools to develop satellite missions. Apologies in advance if you've heard any of this before. I am part of the relatively new Center for Space AI set up at the University of Bradford here in the UK, and we have only recently started working on our PocketQube mission. So these are our first steps and something we wanted to share with you. As like I said, we are based in Bradford. We are fairly lucky to have a good suite of facilities available to us at the university. For example, we've got an anechoic chamber. We are building our own ground station. The center itself is being supported by the Satellite Applications Catapult here in the UK, and we have established good links with industry partners like Airbus, Thales Alenia Space, Filtronic, and others. Even though we only officially launched in October, so like a couple of months ago, research activities at the University of Bradford related to space and satellite systems have been going on since the 1980s. Most of those have a very electronic engineering or wireless communications aspect to it. Again, like the people who are currently affiliated with the center, our background tends to be RF with a splattering of like higher layer protocols. We've got a bit of computer science, a bit of AI machine learning. But we're also trying to branch out into other areas, for example, energy. One thing we are interested in from a research perspective is a space-based solar power, for example. Being part of a university, we are also delivering a master's in satellite systems engineering, which currently is being the actual people doing the lecturing are all external experts that we have good links from, and they come from organizations like Eutelsat, and again, Thales Alenia Space, and Satellite Application Catapult, and so on. I hope our website is visible there, but if not, if you just search for Bradford Space, you should hopefully be able to see us. Please have a look, please get in touch. This thing here is more of a internal marketing shot, and it's a model of the PocketQube that we want to build and launch hopefully sometime in 2024. My colleague Muhammad Ali, who is in the audience, he's developed this, and we are iterating on that now. And on the topic of making the actual thing that will go into space, I want to talk to you about mission design. And what do I mean by mission design? Right. So I assume you've seen or heard of the traditional phases in spacecraft development, which are shared amongst all space agencies. This is like the traditional old school way of developing satellites, broken down into phases that can take anything from 2 to however many years James Webb Space Telescope took, which was many. But that's a very systematic way of designing satellites with a lot of design reviews built in, a lot of testing, a lot of verification and validation. Basically, every triangle that you see there is some sort of a document or some sort of a review process that takes place to say, right, yeah, this satellite will do its scientific mission or its commercial mission. So these things, they go, as you probably know, go way beyond just designing the hardware or designing the firmware for a satellite. They include things like essentially what are we doing and why are we doing it? Why are we launching a satellite in space? What is it there to do? Say, for example, we want to measure the magnetosphere around the Earth and see how it varies with seasons or with solar activity. Therefore, we need to launch into such and such orbit, sun-synchronous, most likely. And those decisions, those requirements, those choices, they feed into a lot of what we need to do in order to design our satellites. So they feed into what sort of orbit are we going to launch in? From there, how often, when are we going to have contact with our ground stations? How often, for how long are we going to be in Earth's shadow? How do we design our power systems from there? Do we need to point our solar panels at the sun? And it just goes on. It goes on and on and on. And as you know, as you well know, it is a very complex, very complicated process that can easily and quickly spiral out of control. For example, so I myself, I come from a very much RF background, so things like antennas, link budgets, building transmitters, receivers, that's my bread and butter. So earlier this year, when I was talking to Kais for the first time, and he sent me a link to potential launches on Vega, on Vega C, they all say things that initially don't mean much to me as an RF engineer. So things like, yeah, it's a sun-synchronous orbit, it's an altitude of however many kilometers, but then what does LTDN mean? It doesn't mean London, which I don't know why I thought it meant that, but yeah. So these are all parameters that I wanted to know how they affect, how would they affect my ability to communicate with my satellite. And all of that led to some other questions such as, which one of these is best? Assuming we have a satellite ready and working, and we've all tested and we're perfectly happy with it, how do we know which one of these to go for? When will I have contact with my satellite? For how long? What part of the Earth is my satellite going to fly over? Things like when, how often? And again, the topic of solar panels and batteries and keeping things in check is when will I be able to recharge it? Can I plan for having enough power at the right time and for the right length of time? Later on, I will show you what happens if we, say, pick an orbit that in the second quarter of 2024, which is when we are hoping to launch our satellite, and it's at an altitude of 650 kilometers and has a local time of descending node at 10:30 in the morning. So how do we go from knowing the orbit, for example, knowing the orbital parameters, and knowing what we want to achieve once our satellite is in space, to getting answers to all those other questions? There are so these are the usual tools that you might use, not just to find answers to those questions, but also to then design your satellite, design the PCBs, design the antennas, design the mechanical structure, make sure it doesn't overheat, and so on and so on. So yeah, you've got SDK, you've got FreeFlyer, which despite the name is definitely not free. It is a commercial proprietary solution. You've got CST, which is brilliant for antenna design. Katia, which is Dassault Systems software, which has everything in it from mechanical design to thermal to model-based systems engineering. ANSYS, whether it's for designing antennas again, or designing high-frequency circuits, or designing just regular PCBs, and also integrating all that with SDK. And then Altium Designer as an example for a paid PCB software. All of these are really, really good, and all of them are very, very proprietary and very, very expensive. Now, we have the luxury of being able to afford teaching licenses for some of these, so we can teach our students how to use them, things that are used in like the traditional satellite industry, and things that could help them get a job. However, we've not got a license to use those for our research needs. So then the question is, what are the alternatives? And this is where open source comes into play, because virtually all of those pieces of software that traditional and new space have been using for decades to design their satellites and to make sure that they fly true and they achieve what they need to achieve, they do have some sort of an alternative. Now, I say some sort of an alternative because it's not always a like-for-like comparison. So these are all the different pieces of software or libraries that I've had to essentially wet my toes in to find out, like to be able to recreate the things that you can do with the commercial packages. So starting off from the top, I'm not going to talk about KiCad and FreeCAD because I assume those are fairly popular, and I assume a lot of people use them. But yeah, there are electronics, PCB design, and mechanical design, including thermal modeling. FreeCAD is wonderful. At the very top, at the top left, we've got the general mission analysis tool, which I'll do a short demo at the end, which is the tool used by NASA it's developed and used by NASA to model orbits and to model orbital maneuvers, things like thrusters, interplanetary travel, you name it. We've got the combination of Gaffer, Modelio, and Capella, which are there for model-based systems engineering, and they can help you stay on top of things like what do my legislators need me to provide in terms of data for my licenses. So what does ITU want? What does IARU want? What does Ofcom here in the UK want? And so on and so on. ORCID is something that I myself am particularly keen on. That's a very low-level library that essentially allows you to build your own space dynamics tools. It's unfortunately for me written in Java because I don't speak Java. I can't program in Java, at least not yet. But it's it was developed and used by the Swedish Space Agency, and it's still used by a lot of companies. In addition to that, there are a lot of Python libraries. As you can imagine, PolyAstro, for example, is very good for visualizing simple orbits and potentially teaching kids about how to, like what happens when with them. We've got things like Open Elevation is a very good website with an API that lets you find the altitude above mean sea level of a particular point on the Earth's globe. And for people who've had to do link budgets or compute like elevation angles and whether or not you can see your satellite, this is a godsend. Normally this sort of data is, again, proprietary and paid. OpenEMS, GPIMax, and ForNec2 are there for people who want to design their own antennas and make sure that if you're experimenting with a more complicated design, they're there to essentially you can make sure that your antenna design would work, your installed antenna design would work, because antennas don't always behave the same way when you test the antenna on itself or antenna on a spacecraft. And honorable mention for QUX, which is there for high frequency circuit design. All of these pieces of software, they inevitably they use data from somewhere, and this is my non-exhaustive list of essentially repositories and places where you can go and see if someone else has already done something that you need. NASA and ESA have a lot of wonderful tools, but those are slightly caveated. NASA's, for example, and some of the better ones are not available to anyone who is not a US citizen. ESA, their code repositories, they require you to have sign up for a login, and I'm not 100% sure on the eligibility criteria of those. And while some of their code is open in the sense that you can have a look at it, it targets proprietary platforms, so it targets their microcontrollers, their radiation-hardened, radiation-tolerant, space-qualified ones, which we may not have access to. But again, they're a very good source of something we can learn from to how we can design better firmware for our own PocketQubes. Various standards like ECSS, CCSDS, and ITU are now freely available. A decade or so ago, a lot of these used to be behind the paywall, but thankfully, as the world moves to being a more open, more connected place, these organizations have recognized the value of making it available to anyone. And again, those are things where we can go and learn best practices from. A lot of the open source tools and a lot of the open source frameworks that were on the previous slide, again, as well as others that I either missed or forgot to include, they essentially use and implement a lot of these standards. But I'm particularly keen on, I particularly like LibreSpace Foundation. SatNox was mentioned a couple of times ago. LibreSpace are the people behind it. Basically, they have other open source projects on their website, including an example implementation of a PocketQube with communication systems and some firmware. So again, an excellent source of learning and of building upon. Open Source Satellite Program is a UK-based initiative which has a slightly different sort of mission to them. So while they are making all of their resources available, all of their reports and things available, they are still targeting more commercial, more established use cases. However, you can look up reports on their website about how, for example, like if you just put, say, an Atmel 32-bit microcontroller in space, how will it fare depending on how much radiation it gets? They also have a wonderful video on their YouTube site of how you can use Blender, as in the 3D modeling program, to see when your when and how much your solar panels will be exposed to the sun and at what angle. So if anyone's interested in finding out, like what sort of angle I'm going to get, how much power I'm going to generate, you can use Blender, the 3D modeling software, to get like a first order estimate of that. Some pros and cons, I think I've already mentioned. So a lot of them are free. All of them are free. You just don't pay with money. You pay with your time, and sometimes with wondering why something is not working. You do need to write a lot of glue code to bring all of these things together to achieve something that normally in a commercial solution you just do with a few clicks. However, there is a lot of community support, there is a lot of very good spirit in those, and again, these are things that anyone and everyone can download and can have a go at. So, for example, if you are trying to reach kids at schools, or you're trying to, again, like teach students and you've not got enough resources to afford a commercial solution, these are already there, and they're just as good. There are some, ironically enough, GMAT, the NASA software, doesn't work as well on Linux as it does with Windows, which I found counterintuitive. But yeah, unfortunately also some projects sometimes just get discontinued, so if you do get involved, invested in open source a lot, my recommendation is to either be able to offer in-house support, or contribute to the project so that it sticks around. And unfortunately, sometimes the solution might just not exist. Now for right, so GAFOR allows you to basically bring together, like have loads of different diagrams that often get very, very large very quickly and very ugly, but they help you track things like where do requirements come from, what sort of institution requires what sort of data. It helps you do things like essentially sequence diagrams. So for example, if you're planning your mission, when do you fire your thrusters, when do you communicate? And then lets you tie those things really well to verification and validation plans, design files, and so on. And the beautiful thing about all of these is that they are text-based, so you can just plug them in whatever version control system you're using, and again, make that public, share it with people, and then people can follow your progress. And now a very quick show of what GMAT looks like for if no one has. Oh, Right, has anyone used GMAT before? Okay, cool, right. So, did you get to use the OpenFrames interface? Does it work well? Did anyone get to do it under Linux? No, yeah, it's just a blue ball, isn't it? It's bizarre. But yeah, so the things that I, again, coming from an RF background, that I really like is that once you run either the mission or the simulation of the mission, you can see like where your satellite goes, when it goes. You can define base stations wherever you want with their corresponding local coordinate systems, which then makes it very, very easy and straightforward to get reports such as this wall of text, which basically so yeah, apologies. Basically, we get to know where the satellite is, when the satellite is going over places. From there, we get to see we can get to see when our satellite will have line of sight to our base station, and from there we can take all of that information and do our link budget, which in our case is important because we're building our own ground station, so we need to know what sort of hardware we need to get, how much amplification we need, what sort of bit error rates we might get, what sort of signal-to-noise ratios we're going to get, and so on and so on. And GMAT helps us do that when combined with some of the other frameworks, like Polyastro, which is good for various orbit manipulations, ITUR-Pi, which helps with things like atmospheric attenuation, gases, and all sorts of wonderful things that you normally need to add to your free space path loss. But unfortunately, this is still work in progress, gluing everything together and being able to essentially press a button and get a report saying, if you do this orbit, this is what you're going to get. If you do this other orbit, you're going to get more contact, for example, contact more often, but you're going to have more attenuation, or if you do this orbit, you're never going to get contact from your ground station. And again, that's why we're doing this. But that's more or less it for me. As a final message, there's loads of wonderful tools where you can have that can help you have a holistic view of your mission and can help you plan so you can then implement, test, verify, and validate your PocketQube. And then when it goes into space, it works. And you know where it is and when it is. So yeah, that's it for me. Thank you. And again, please get in touch. Always happy to talk to anyone and everyone. Yeah, thank you.